ไม่ใช่เป็นหนึ่งนะครับเพราะว่าอันนี้
เพราะว่าอันนี้มันไม่ได้เป็น running มันเป็นเหมือนแค่เป็น confirm กลับมา เพราะว่าถ้าเกิดเป็น running คือต้องเป็นช่วงของ data transfer อันนี้เป็นแค่ใช้ซ้ำกับอันนี้ได้เพราะว่ามันไม่ได้ carry next data
อันนี้คือแบบ just like connection establishment
ใช่ครับเป็น signaling ใช้แค่1 sequence number พอ1 sequence number ถึงจะเป็น2 packet ก็ตามแต่เป็น packet request กับ packet confirm มันไม่มี acknowledgement สำหรับ packet นี้ถูกไหม
อันนี้ไม่มีอันนี้
มันถึงใช้อันเดิมเพราะมันไม่ได้ run เป็น next คือนี่เป็นโปรโตคอลครับมันเป็นถูกบังคับให้ใช้ sequence number ตัวเดียวตัวเดิมแต่ถ้าเกิดเป็น data transfer มัน sequence number มันจะ run ตามอันถัดไปก็ต้องเพิ่มขึ้นเรื่อยๆถูกไหมแต่นี่มันเป็นแค่เหมือน flag signaling ธรรมดามันเลยได้ไม่มีการเปลี่ยน sequence number มันเป็นโปรโตคอลที่เขากำหนดมาครับหลักการโดยที่ไม่รู้ว่าทำไมมันก็คืออาจจะเป็นเพื่อว่าไม่ต้องเป็นต้องใช้ sequence number เกิน1ก็ได้เป็นการประหยัด sequence number เพราะมันมีแค่3 message เองเราส่งไป1เขาส่งกลับมาแล้วเขาส่ง confirm จบโอเค Okay, just to recap the 13. Okay, 13 would be the wide LAN. Okay, so wide LAN Ethernet. Okay, mainly. Hold on. 12? Haven't got 12. 12. Okay. Okay, so 12. Okay, 12 is involved. Okay, we have the main protocols that we use for the layer 2. Okay, the lower layer 2 is the random access and the control access. So basically convolve the distributed concept and the centralized concept. Okay, so distributed concept we use the random access, whereas the control, okay, we based on the central unit or a certain person will control. Okay, so we have Aloha, CSMA, CSMA CD, and CSMA CA. Okay, and Aloha, we have Aloha and slotted Aloha. Okay, so you can you understand what are all the details of those. Okay, Aloha, we don't listen to the or sense the carrier before we transmit. Okay, whereas the slot Aloha, we also don't sense the carrier, but we use the synchronization between the individual hosts to know the starting slot. Okay, so we have to have this very accurate clock between each user to determine what is the beginning of the slot to start transmitting, so that we reduce the variable time, okay, of the Aloha to the lower value of in the slotted Aloha. For the CSMA CD and CSMA CA, we talk about the case that the host would be able to sense the carrier or listen to the carrier before they can transmit. Okay, CSMA, we can sense and transmit, and mainly we wait for the acknowledgement. So you can see it takes longer before they realize that the previous frame that they have transmitted is useless if they don't receive the acknowledgement back within the timeout period. Okay, so that is CSMA. Whereas CSMA CD, okay, we have ability to detect the collision, but in order to detect the collision, it means that you need to be able to continue transmitting the frame while you monitor the incoming signal. Okay, if you finish transmission before there is incoming signal, you might not know whether or not that incoming signal has collided with your transmission. So that's why we can use this concept that variable time for the case CSMA CD is longer than the CSMA. Okay, because we have to wait until the extreme case of message from the other end arrive at you. So this is why we need to calculate the minimum frame size. Okay, minimum frame size for the technology that you use in the CSMA CD. Normally it's an Ethernet. Okay, so we determine the minimum frame size to be 512 bits, right? Okay, based on 10 megabit per second, and the segment length we have determined. So we have, okay, the propagation time, 2 times propagation time. So CSMA CD. Whereas CSMA CA is a wireless LAN. Okay, so wireless LAN mainly we don't have collision detection capability because we use the airspace. We don't have the wire that is incoming and outgoing or send and receive as in the UTP in the case of the CSMA or the coaxial in the CSMA CD. So in CA, we use the collision avoidance concept. So that collision avoidance concept is based on IFS period, okay, interference space period, that we wait a little bit longer after they finish the previous transmission. Again, before we start transmit, you see that all algorithm in the CSMA-CA, we have to wait IFS period. Okay, you can look in the flow chart. Okay, that a lot of IFS. Okay, could be DIFS, SIFS, or PIFS. Okay, that would insert it. Okay, as a pause, short pause before you transmit. Okay, so that would avoid the collision with the previous transmission or other transmission. Okay, so that's the reason we call the collision avoidance. Okay, for the case of the okay, that's, I think we all talk about that. Okay, so you check out the variable time, okay, and also the how each individual protocols, okay, were achieved, okay. And we have the control access where mainly we have the reservation, polling, and token passing. Okay, so basically we're going to have a certain person or a certain things that would control the access. Okay, that would be a person granted the access or assigned, okay, the slot for the access, or you may have to previously request, okay, in the request frame, okay, before you can transmit. Okay, so this is a different concept from the random access. Okay. And we didn't go into the channelization. Perhaps so channelization, I leave that for the telecom subject. Okay, so we have the chapter 12. Okay. Any question on chapter 12? Okay, so for 13, okay, 13, we talk about WLAN. Okay, so WLAN basically we're going to discuss about the layer 2.1 and 2.2, and mainly would be 2.1, where is the medium access control sublayer, the lower sublayer. Above sublayer would be logical link control. Okay, some textbook may call DLC, digital data link control. Okay, so we have the terms of standard Ethernet, fast Ethernet, gigabit Ethernet, and 10 gigabit Ethernet as the standard Ethernet that we use today. So 10, 100, 1, okay, 1 gig is 1000, and 10,000, which is 10 gigabit per second, would be the speed of the Ethernet. Okay, and we have looked into the header of the MAC layer. Okay, in this one we see the two. Okay, if you compare this one with the 802.11 wireless LAN, you will see the format of the frame is different. This one is one we use in the wide environment. Okay, in 802.3. Okay, 802.3, which is Ethernet, Ethernet standard. Okay, so we have only two address, destination and source address. But if you remember 802.11 frame, we have 4 address field, right? 4 address field that is different from 802.3. Okay, so this one we look at the length of the address or the format of the address in layer 2. Okay, normally it's 48 bits or 6 bytes. Okay, 6 bytes long, and normally written in the hexadecimal format. Okay, and we introduced the concept of data and padding. Okay, because the padding would be required if we have a too short packet. Okay, because if too short packet or too short pin thing that fit into the frame size would be smaller than 64 bytes. Okay, so we have to make sure that minimum frame size is 64. Okay, because we have 14 bytes of the header and 4 bytes of the trailer. So add with 18, okay, and 46 would be the minimum size of the payload. Okay, so we have to make sure that data plus padding would be 46 bytes. Okay, so eventually it would make the frame size to be minimum of 64 bytes. Okay, so that is the length of the frame. Okay, in the Ethernet case. Okay. And also, we could indicate the type of the address, okay, to be broadcast, okay, or to be multicast, okay, this one, or unicast, okay. So basically, it's the last bit of the first byte, okay. And what else? okay, and the format of the address, okay, and also you look into the name of the standards, okay, you can tell the speed, you can tell actually everything is baseband, okay, but the first number and the last letter would determine what is type of the medium, okay, so you can see that we have the number represents the coaxial, represents the UTP, okay, and represents the fiber, okay, so make sure that you are aware of what would be the type of that medium. Okay, and for example, if we have standard Ethernet, okay, standard Ethernet, we would have the coaxial and the UTP as well as the fiber. Okay, and normally when we talk about the standard Ethernet, okay, it's the old or very primitive LAN where we're going to use the bus topology mainly. So when it's bus topology, we're going to have the length of the segment. Okay, generally length of the segment will depends on the type of the medium. Okay, so you see that the length, okay, for example, if we use coaxial cable, okay, we have 200 meters, actually it's 180 something. Okay, we have the 10 base 2, and we have 10 base 5 that we use thick coax there. Okay, when you use thicker medium, okay, the length would be go further. Okay, and we have the star topology of using the hub like 10 base T. Okay, and hub again, sorry, the hub of the fiber is 10 base F. Okay, and we have looked into the developing of the new standard of fast Ethernet and the gigabit Ethernet. Okay, before we going to that, we look into the concept of collision domain. Okay, so collision domain will depends on the type of equipment that you have used to connect the equipment or the hosts together, because that determines how you're going to compete to access. Okay, so basically what domain would compete by certain number of hosts. Okay, so this one, it depends whether you're going to use hub, okay, or you're going to use the switch, okay, the switch or router, okay. So in that case, you look at different type, okay, of the domain. If you use switch, okay, the domain will be individual ports, okay, individual ports will be their own domain because you don't have to compete with anyone else. But if you use hub, okay, you're gonna compete with a certain number of users, okay. In fast Ethernet nowadays, we're going to use the switch rather than the hub. Okay, so in this case, the topology that we deploy in fast Ethernet would be star topology mainly. Okay, and in star topology, we have for the fast Ethernet, we have 100 base TX, 100 base FX, and 100 base T4. Okay, don't worry about the encoding. There is no question asking about encoding of the Ethernet. Okay, and for the gigabit Ethernet, okay, we have the higher speed and the topology would comes into more complicated or more hierarchical, okay, structure. Instead of having one star, that would be multiple star or mix of the star topology, okay, where they normally involve the core, okay, core part of the local area network, okay, and we have 1000 base SX, 1000 base LX, 1000 base CX, and 1000 base T, okay, depending on the type of the medium that we use, okay. And the last one is 10 gigabit Ethernet, okay. So we have 10G, okay. So now we don't write 10,000 number, we use 10 and G, okay. 10G base S, 10G base L, and 10G base E, okay. So all of them using fiber, okay. And fiber depending on the type of fiber, but nowadays you see that most of the fiber that we use would be single mode. Okay, remember the first half we talk about multi-mode and single mode. Okay, today most of the fiber is single mode already. Okay, due to the advancement of the manufacturer. Okay, so we don't really have the multi-mode anymore. Okay, to be used in the market. Okay, so these are the chapter 13 where we mainly talk about the standard. Okay, how we define the standard, what is the meaning of the standard, and collision domain. Okay, because if we use different equipment to connect the local area network, okay, the major things that you have to be concerned with is how they're going to compete to enter the medium. Okay, so that's the medium access control. Okay, and 14, okay, so 14 would be dealing with the wireless LAN. Okay, as we have seen now is wireless LAN, the medium would not be the wired. Okay, it's going to be open airspace. Okay, so that would utilize the radio frequency. okay, as the medium. So topology of the wireless LAN, as you can see, we're gonna be, okay, two main types is either the ad hoc or infrastructure. If you have infrastructure, everything have to be connected via the access point. Whereas the ad hoc mode, okay, they'll be directly connected to one another to have the connection to communicate, okay. And if you have the one access point connected to several stations or several hosts, we call this is basic service set, okay, BSS. But if we involve multiple access points, okay, as you can see, connect via the wire distribution system, okay, this called multiple service set, okay, or extended service set, sorry, extended service set or ESS that combine several access points together. And you can see some area, the computer may be able to connect to more than one access point, okay, so that allow mobility. And in this chapter, we mainly look at in the MAC sublayer, okay, MAC sublayer. You see that in the 802.3, the MAC sublayer is not really the main concern because if you are using switch, CSMA CD is not your protocol because you have your own domain, right? If you use switch, but if you use hub or if you use bus, you require CSMA CD. Okay, so if you look at Y type, okay, Y 802.3. But if you switch, we don't use CSMA CD. We just use individual connection through the switching fabric, through the processor to the output port. So you have your own domain. You don't compete with anyone. Okay, we use switch. So CSMA CD used only in the bus topology, okay, or hub, using hub topology. Okay, but in the case of wireless LAN 802.11, now the topology would be basically bus topology, right? Even though it looks like you're connecting to the access point, individual connection, but inside the airspace, you are using the same frequency, 2.4 gigahertz or 5 gigahertz. Okay, so in that case, you share the common channel. Okay, so you have to take turn or find a certain kind of medium access control to control the access to the access point. Okay, so even though it looks like you are star topology from your host to the access point, but actual thing is the bus topology because everyone share the medium. So that's why medium access control play an important role in 802.11. Okay, because everyone send with the same frequency, you will collide anyway. Okay, what we have to do, we use two concepts of medium access control for wireless LAN, which is PCF and DCF. Point coordination function and distributed coordination function. Remember, we have DCF, the pink one, and PCF, the blue one. Mostly the default method is the DCF, where basically it's based on CSMA-CA. Okay, CSMA-CA can resist multiple access with collision avoidance. This is the DCF, okay, distributed coordination function, where everyone control themselves, listen to the air and transmit. Okay, whereas the point coordination function is take place, okay, repetitively, okay, alternate between PCF and DCF, PCF and DCF. When it's PCF, it means that the access point taking control of the access by the host. So in this case, access point will grant access to someone, okay, through the polling method. Okay, so generally most of the time, okay, most of the period, everyone controlled by using CSMA to enter the airspace, okay, to transmit. But from time to time, there will be repetitive process, okay, like this slide here, okay, that we alternate between PCF and DCF. Okay, so DCF distributed, it means everyone control themselves. PCF point means access point control access. Okay, so that would be the process inside this slide here, where the access point will poll, okay, who will be allowed to access, who will be allowed to send. And later on, once this session finish, we'll enter the. You see that we have the period called the contention free and contention. Okay, so contention free is PCF. Contention is DCF. Okay, so it's alternate between these two things. Okay, so alternate between contention free and contention period. Okay, and whenever they see the station here is the RTS, okay, we set itself to network allocation vector or NAV. So NAV basically is a silent period or a timer that we have set to be in the silent mode. Okay, because that someone is talking. Okay, you have to be silent to avoid collision. Okay, and we use the RTS TTS to confirm, okay, the transmission. And you can see that every time that before you transmit, you have to wait IFS period. Okay, interframe space. Okay, period here. Okay, and again, frame format, I mentioned here that we have 4 fields of the address. Okay, so true address, okay, or that current source and destination and the true source and true destination. Okay, true source and true destination would be indicated in the field number 4 and number 3 and number 4. But for the current message, where it's from, where is the 2 will be sent in the destination address 1 and address 2. Okay, so we have 4 different mode of the addressing usage. Okay, so that one depending on the addressing mechanism or where that message is traveling from the station to access point or station to station. You see that case 1 is for ad hoc case. Case 2, 3, and 4 is for infrastructure case. Okay, whereas the case 2 and case 3, the real source and real destination will be indicated in the address number 3. And whereas address case 4, okay, we use all 4 addresses. And particular things that we have to pay attention is the distribution in case 4 is the wireless distribution system. So it means that there will be transmission between access point to access point. Okay, so the format of the frame would be in the wireless form. Because if the yellow thing is wide, we're going to use the frame format that is 802.3 rather than 802.11. 802.11 used in the wireless environment. 802.3 used in the wide environment. Okay, so we use different frame format. Okay, and in this one we have talked about the 2 situations that normally cause problem in the wireless environment. Okay, the hidden station and the exposed station. Okay, so hidden station, you know what it is. Okay, and normally we use the RTS TTS to help, okay, avoiding this problem. Okay, so the other one would not send, okay, the message to have the collision at a certain point. Okay, so we use CSMA CA to handle the problem. But the other situation is called exposed station. In this one, RTS TTS might not help. Okay, so we may have to use other techniques like, for example, use directional antenna, which is not really practical, okay, in use. Okay, so this again, okay, will be the one that reduce the efficiency, okay, or utilization of the network, okay, because actually C want to transmit to D, but C cannot do that because C here the transmission of A towards B. Okay, so C is exposed to transmission of A. Okay, so actually C, if the C can avoid this exposure, we can send it to the D, okay, without a problem. Okay, but this is not the case. Okay, and we have example of the physical layer standard of A, B, and G type, okay, of the band that we use. Okay, 2.4 and 5.7 gigahertz. Okay, and we don't go into the physical encoding. Yeah, so don't worry about the encoding. Okay, and a little bit on Bluetooth. Okay, Bluetooth, what we have to be aware of is the structure of the Bluetooth. Okay, in the Piconet, Scatternet, okay, that we have talked about here, and the protocol layers. Okay, protocol layers basically is not the same as the OSI, but it try to make a reference to the OSI by using the baseband layer and L2 cap layer, okay, as the MAC and RLC sublayer. And the connection of Bluetooth, as we mentioned, is profile required. Okay, so we need to write the profiles that what particular type of this Bluetooth connection is for. Okay, so the process, okay, will take place differently for different profiles of the Bluetooth connection. Okay, and we have the TDM mainly, okay, to transmit the data between the primary and secondary. Okay, and if we have multiple secondary, it would take turns, okay, to assign the slot for the secondary towards the primary. So this is for the case of single or multiple secondary case. Okay, and the frame format, you don't have to remember or memorize the details. Okay, so this is 14. Okay, wireless LAN. Okay, the standard. Okay, the access protocol and the problems with the hidden and exposed. Yeah, that's 14. 19. Okay, I think 19 would be talking about the IP address. Okay, so IP address would be, I think, 32 bits. Okay, so you know how to convert between binary and secondary. And we introduced the classful address. Okay, the classful address normally will be the address that hopefully is unique. Okay, for a particular organization that obtains such class of IP address. Okay, in classful we have fixed the bytes that would be the network portion, where you cannot change that particular yellow portion. Okay, class A, class B, and class C, and we can determine the class based on the first byte. Okay, the value of the first byte. Okay, so we have the range of the first byte. Okay, of class A, class B, and class C according to the value in decimal of the first byte, or the number of bits, several bits in the first byte. Okay, and I think you know how to work out what is the first address and last address of a certain block, based on the masking that we have given. Okay, so this one, okay, example of how we put the mask. Okay, how to determine the first address, last address. Okay, and how we assign the address to individual hosts and the network. Okay, if we have a block of address, as I mentioned, the first and the last were reserved. Okay, the first is used for network address, so you don't assign to anyone. And the last address of the block normally would not be assigned to anyone as well, is for broadcast. So normally the address availability of that particular block would be 2 to the power number of hosts minus 2. Okay, minus 2 because the first and the last were reserved. Okay, to be assigned to the. Okay, so if you divide it into more subnet, you're losing more address to the first and the last in the block. Okay, so that could be one of the problem. Okay, and we have the discuss about how we're going to assign the IP address to several group of users. Okay, according to their requirements, the number of hosts for that network. If we have many users in that group, okay, how we're going to divide that. And also we normally design based on the contiguous address, where address block is connected together. Okay, so we're going to arrange the address, okay, in the contiguous form. Okay, and we have the private address. Okay, so don't have to memorize the details of the private address, but mainly we have one block from class A, one block from class B, and one block from class C reserved as a standard. Okay, so we normally use and adopt that. Okay, and we have also the concept of NAT, okay, network address translation, because as we say, in Fly organization, we may have the requirement of a lot of hosts connected to. But with the classful address that we obtain, it might not be enough for everyone in your organization. So everyone in the organization will be assigned with the private set of IP address. So when you go out, your source address have to be exchanged into the public address. Okay, so there will be a lot of users share the same public address. Okay, so when come back, okay, the gateway which contains the NAT function will re-change the IP address that normally the public into the private again, based on various tag, okay, various flag, okay, that could appear in this table. Okay, so the NAT translation is located inside the gateway. Okay, so the gateway will work out what is going to be the public address, and when it's get inside, what is your private address that you use. Okay, and a little bit on IPv6, where we have talked about the length of the address, 128 bits long, and the format of writing that going to be the colon form. Okay, so we have to have 8 parts of the separate with 7 columns. Okay, to be 8 parts, and we have the abbreviation IPv6. Okay, so you should be able to form the abbreviation if you have a certain set of IP address version 6. Okay, And the table, don't worry about the table and the format. This is the chapter 19. Okay, chapter 19. Okay. Any question on 19? And 20, okay, would be involving the internet protocol. So this one, once we know the IP address, what we have to do is we have to know the function of internet working when we connect multiple networks together. So in this one, we have to understand the concept of switching and routing, as we have discussed so many times. Okay, you see that the starting point and end points of each layer. Okay, for layer 2 is start and end at each hop. Okay, the information created and information terminated would be at each hop for layer 2. For layer 3, the termination, the starting or the creation will start at the source and will be used for the entire routes that we travel until it will be terminated or removed by layer 3 at destination. So in this one, we can have, okay, repeat the concept of link between the host and also the network layer, okay, in an internetwork. Okay, internetwork is this one. Okay, when we go across the router, we enter the new network. Okay, so the router will perform this. Okay, and we talk about the function performed at each position, at the source, at the destination, at the intermediate nodes. You see that for the source, we're going downwards from 4 to 3, 3 to 2, right? For the destination, we go from 2 up to 3, 3 process the routing and go to 4. Whereas the intermediate node, okay, we have 2 to 3 and then down to 2 again. We're not going beyond layer 3 because layer 3 perform the routing calculation or routing process, okay, and know that which interface output that we're going to forward out. Okay, so that is the layer 3 function of the intermediate nodes. Normally it's the routers. Okay, and IPv4, okay, so now we look into the header of IPv4 of several fields inside the header. So the base header, we have the 5 rows, okay, 5 rows is 20 bytes, okay, because each row is 4 bytes. Okay, so the third and the fourth and the fifth rows is the row that we put the IP address version 4 for the source and destination. Okay, and before that, row 1, number 1, number 2, number 3 would contain the several fields that are useful for their forwarding this packet. Okay, so again, don't worry about the code or the bits or the value. Okay, that represents different protocols or different meaning. We're not going to ask that. Okay, and we have some example of calculation of the total length based on information in the header. Okay, like the length, header length, total length. Okay, header length represents the number of rows, right? Okay, the value represents the row. So you have to multiply by 4 to know the number of bytes. Whereas the total length is the value of bytes in itself. Okay, so you don't have to convert anything. Okay, so we have the header here, right? So the total length here and the header length here, right? The total length is the byte value. The header length is the row value. Okay, so in order to calculate the body part, you have to change the header length by multiply by 4 first. Okay, so this is the main point here. And okay, and also this we have already mentioned about MTU, the maximum transfer unit. This is the reason why layer 3 perform the fragmentation. Okay, in order to fit into the several MTU required by the technology that you use as a network, okay, to carry your message. In this case, we concentrate on the Ethernet, right? Ethernet, the maximum transfer unit is 1500 or 1500 bytes. Okay, so what is the maximum frame size of the Ethernet? 1500 plus 18. 18 is come from 14 of the header and 4 of the trailer. Okay, go back to the frame that we have talked earlier. Layer 2. Header, what do we have header? Header of the frame, we have source address, destination address, right? Okay, and the other field. Okay, and the last one, CRC, would be the 4 bytes. Okay, so altogether it would be 1500 plus 18. So the maximum frame size would be 1580. 1518 bytes. Okay, that's why we need to chop it into certain size. Okay, we call fragmentation to fit. Okay, generally fragmentation would be smaller, a little bit smaller than the maximum transfer unit. Okay, so because we don't want it to be like maximum. Okay, and you can see that we can fragment further. Okay, if you wanted to. Okay, in that this one, and we have the example also mentioned about the M bit. Okay, M bit is more, right? More bit. Okay, more bit. Whether we have more fragments coming after this. And again, we have the calculation of checksum. Okay, checksum in this case, we use the content of the header. Okay, in the header of the packet. Okay, calculate the sum and turn that into complement of the sum. So this value would be the checksum that we fill back into the checksum field. Okay, and for the case of IPv6, okay, in IPv6, what we want to look into is basically the length of the packet. Okay, so for the packet, we know what is the base header and what is the maximum length header of the IPv4. IPv4, what's the maximum length header? How many bytes? Minimum is 20, right? Maximum is 60 bytes. So it will be 40 extra bytes as an option. Okay, how many extra rows we can have? 40 bytes mean we have 10 rows extra as an option, right? For header, we have 20 is base, 5 rows. So we have 60 bytes, mean we have 15 rows of the header for V4, right? But in this case of the V6, okay, 40 bytes would be the base header of V6 because we have 2 rows of other fields and row number 3, 2, 3, 4, 5, 6 is for source address and 8, 9, 10, 11 is for that 3, 4, 5, 6 นะครับ 7, 8, 9, 10 is for destination address. Okay, because we need 4 rows to fit 128-bit address. Okay, so this is the header. Okay, so this 40 bytes, okay, would be 10 rows. Okay, 10 rows. Okay, 10 rows of the header. Okay, and okay, again, the table, just skip that one. And we have the transition, but the transition basically is how we're going to make the V4, okay, coexist with V6. Okay, so we use 3 main concepts, the dual stack. Dual stack means the equipment that would possible run this or connect to this network would capable of 2 protocols. Okay, so each individual port of this equipment must be able to perform IPv4 hacking or IPv6 hacking. Okay, whereas the case of the tunneling, okay, we're going to use some kind of encapsulation concept. Okay, so the body of IPv6 packet, okay, would become the body of IPv4. And we add the header of IPv4 into. So this would become the IPv4 packet. And the other one would be using the header translation. Okay, we take some information IPv6 and translate that into V4 header. Okay, and the payload would be the same. Okay, this payload would be the same thing, but we just change the IP header. Okay, for the case of header translation. Okay, so payload are the same throughout this network. Okay. So this is chapter 20. Okay. So 22. Okay, the last one that we're going to revise here. We have the already concept of network address. Okay, IP address. We talk about the concept of the packet format, the header format. Okay, and now we talk about how we deliver, how we forward, and how we route them. Okay, so delivery. Okay, remember we talk about 2 cases of indirect and direct delivery. If you have direct delivery, the location of destination are in the final destination, so it would be from gateway to destination, or source and destination are in the same network. This is direct delivery. Okay, the source and destination are the true source to destination. Okay, this is the direct delivery. Whereas the indirect, okay, indirect is basically the first hop or the middle hops of this communication, because the first hop you send to gateway, your default gateway. The middle hops we send to the intermediate gateway hop by hop, and the final hop would be true destination. So that is the final hop would be direct delivery. Okay, and the forwarding, we're going to forward based on the information inside the table, where we adopt the network specific and next hop, okay, address concept. Okay, so the aim is to minimize the size of the routing table. Otherwise, the routing table is going to be really, really large. Okay, and the basic routing table normally involve 4 fields. Okay, the mask, network address, next hop address, and the interface. Okay, I think we have talked about this. Okay, and we adopt the classless because now we can assign the mask, okay, according to your requirement. So we have the slash notation accompany the IP address. So this we call the classless. Okay, so we don't care about what class this belongs to. And normally we use this classless concept with the private IP address anyway. Okay, so with the private IP address, you can use any class masking length, okay, to use. Okay, so we have the okay, the classless concept and also the routing table. Okay, the main thing is if you have the local network connected to that router, normally we require to provide individual network, the local network in the table, because individual network would be connected to different interface, right? So that's why we need to indicate clearly if it's the local network connect. For example, this router number 1, we have 4 local networks connect via different interface. So we need at least 4 rows, okay? And normally when we put in the rows of the table, we put the longest mask first, okay? Longest mask come first, because when you do the routing, we normally take the address and do the masking process row by row, okay? There could be multiple matching in this table, but we'll pick the longest mask matching. So the longest mask matching will give us the most specific or closest to the destination for us. Okay, so we have the local networks, and again, the final rows need to be the default rows, where if you couldn't find any address, we're gonna send it to the default rows, which is the default gateway. Okay, so we need to provide the default gateway in case we know that, right? But in example, you may see that we use dotted line. Many dotted line appears in the picture. Dotted line means it's like a cloud. Okay, so we don't know the address yet. So we just leave like a question mark or the dotted line. Again, the information to be filled later. Okay, an example of this page 22.7, it talk about aggregation of the address. Aggregation of address, you see that the table of R1 here need to be at least 4 rows for individual network through different interface, plus the one that is default row, which is if you couldn't find anything, we will send through these default rows again to the rest of the internet. Whereas in the case of R2, you see that there could be a cloud in the middle. So you see that we have, from perspective of R2, okay, in order to send to this big block of address, is all go through the M0 interface. Okay, that's why we can combine them in the address aggregation. Because no matter which organization on the left-hand side, from R2, we have to send all through the M0 anyway. So we can combine them together to be one single address with the shorter mask. Okay, the shorter mask means the network is bigger, right? So this we combine. But if some part of this aggregated network located somewhere else, okay, we need to indicate that clearly. Okay, because if you see, for example, I give you to try .200. When you put .200 in the router number 2, you see the match 2 rows. Okay, match 2 rows, but you will pick the one with the longest mask because it will bring you to the accurate location. Okay, because if you pick the second row, it will forward to the left-hand side towards the R1, which is incorrect. So if we have the address aggregation and if part of the address on that big block is somewhere else, you have to indicate above, okay, with the longer mask. Okay, so the longer mask will be bringing it to the closest direction. So this is the concept of longest mask matching in case of 22.8 นะครับ so this is longest mask matching and what else? Okay, and we talk about unicast routing protocol. Okay, so unicast routing protocol, we have two main concepts: the interdomain and intradomain. Okay, so we look in intradomain as the requirement for the cost. Okay, so intradomain we have distance vector and link state. Okay, so as the video suggests that we have the distance vector. The concept of distance vector is you gather the information locally and form the initial table. Okay, so in this case, we have the table that contains destination, the cost, and the next stop information. Okay, three basic columns required. This is the final table, but we need to be able to form the initial table, and this initial table would be exchanged with the neighbors. Okay, so the neighbors compare the current table with the information gets from the neighbors and compare that what cost is lower. Okay, the lower cost will be the update for the new table. Okay, and this process repeated, okay, between the neighbors again and again until the value or the entry in the table that don't change. Okay, so that would finalize the table as the table here. Okay, so this is the final table. Okay, and there could be some problem in the case that the update of the status of the network would not be in appropriate order. For example, like in 2-node stability and 3-node stability, you can see that normally if A inform B in the proper manner, like for example, X and A fails. Okay, X and A fails mean that A cannot reach X anymore. And A inform everyone that this link has already broken or fails. B will update immediately that there is no route to X. Okay, so that would go immediately to infinity for both A and B. Okay, if information is delivered to B in a timely manner. Okay, but in this case, when A detects the failures, A tries to inform B, but before A informs B about this failure, B send the update to A. Okay, so this one, A thought that there was a route, okay, to X via node B. So that would start exchanging information because both believes that there could be a route toward X from the information received from neighbors. Okay, so the problem will not happen if A tells B that link has failed. Okay, if A tells B link has failed, B will update infinity immediately. Because this one, because in the situation, eventually it will reach infinity both ends, but it takes a very, very long time. Yeah, because it oscillates between update these two tables. Okay, and it can happen with 3-node instability. Okay, 3-node is going loop as well. Okay, when XA fails, okay, A try to inform B and try to inform C, but B received the information from A, but the information from A to C may be lost. Okay, so C doesn't update the real situation, but C update to B. So B thought that, okay, you can send to X via node C. Okay, so that the process would update in this loop. Okay, so eventually everyone would get infinity, but it takes a long time as well. Okay, an example of this distance vector is like what we have seen here. Okay, the table. Okay, the table will contain 3 columns, right? The destination, the cost, and the next hop. Okay, so the next hop must be indicated clearly that what is going to be the address of the next router. Okay, because for example here, the router number 1, okay, that would have 2 exits. Okay, router number 1 can go to R2, or router number 1 can go to R4. Okay, so in order to go to destination network, you have to mention correctly, okay, which direction you go to. Okay, so this is the table of RIP. Whereas the the link state here that the network or link status must be updated to everyone in the network. Okay, and everyone forms the topology in their head and calculate the routing table, okay, from their knowledge about the network topology. So in this case, the exchange between neighbors is not the table. Okay, it's exchange the link status information. Okay, so link status would be created, okay, and form the topology. And each node will assume itself as the root, okay, as a source. And then using Dijkstra algorithm as the shortest path algorithm to get to each destination. Okay, so this one you see that you can, for example, node 1 or node A here, okay, will form an topology in their brains, in their memories. And then they'll try to form by using Dijkstra, okay, Dijkstra to form the shortest path to the all destination. And this process happened as well in other nodes. Okay, other nodes will have the same topology, but the process of routing will be different. Okay, inside B will assume itself as the root. Inside C will assume itself as the root. Okay, so remember Dijkstra will start projecting from the source or from the root outwards. Okay, one of the main drawbacks of the Dijkstra is we cannot use Dijkstra to calculate the network with the negative cost. Okay, because the concept that we use the cluster from the lower value of level, okay, towards the final nodes. Okay, we will not go back to calculate the cost, okay, if the cost is reduced. Okay, because if the link cost is negative, okay, some cost could be reduced, but this is the drawback of Dijkstra. Okay. If you want to continue that one, okay, please join the teletraffic engineering. Okay, we can discuss about the negative cost shortest path. Okay, and we have the example of the network and try to translate that into the graphical representation. For example, this network here. Okay, this network here, you see that we have the physical representation as we have the black bar as the network and the pink, okay, to like the pink cut pink circle, okay, the oval is the router. Okay, normally there will be link between the network and the router. Okay, we have classified them into point-to-point, transient, okay, and stop. Okay, for the transient and point-to-point, normally we assign bidirectional arrow, okay, to the link. Okay, whereas the stop network is the far end of the network. We have only arrow in one direction towards that network. For example, this stop network is N2, okay, N5 and N4, right? You can see that the arrow signs toward N2, N5, and N4 is only one direction, okay, towards that network, because network will only be destination, will not be the source. Okay, the source will start from individual router. Okay, other network like network 1 and network 3, okay, it could be the intermediate node and could be destination. So the direction of the network that comes through different router may have bidirectional. You can go in, you can go out, can come in or go out from that network. Okay, so that's why the transient and the point-to-point is bidirectional. Okay, because in Dijkstra calculation, we need to have the bottom topology in their memories before they calculate the shortest path. Okay, and each of the link will have the cost associated with it. Okay, so they're gonna calculate the source from the router towards the final destination, which is all 5 networks there. Okay, and we have the interdomain. Okay, interdomain. So basically, we involve the routing between autonomous systems. So we need to have the border or boundary routers, okay, that perform the link between autonomous systems. So this is what we call the BGP, border gateway protocols. Okay, we're not going into details of the interdomain. So this is example to show you that we have different algorithm or different protocols, okay, for interdomain, because it involves, okay, different ownership, okay, of the network. Okay, and normally each of the autonomous system would have the main routers, okay, that connect with the other. And for multicast, okay, I'm not going into much details, but what we want you to aware of the multicasting is basically the comparison between unicast, multicast, and multiple unicast. Okay, because unicast is one-to-one anyway. We have one packet generated from the source and deliver via routing protocols towards the destination. Whereas the multicasting, the packet would be generated once, okay, only one packet from the source. But in the multicasting, we have multiple receivers. Okay, multiple receiver would belong to a group. Okay, so the addressing scheme that we use here is not individual address. We're going to use the common group address, which is the class D of the IP address version 4, which is multicasting. Okay, and in this one, you can see that every router must be aware of where the location of the members. So in that case, when the multicast packet arrives at the router must know how to duplicate the message appropriately by forming the tree, branches of the tree towards all the destination. So if you compare with the multiple unicast like this page, you can see if multiple unicasts means if you have 5 receivers, there are going to be 5 packets generated by the source. Okay, that will be individual unicast, one source, one destination, one source, one destination, one source, one destination. But if you use multicasting, the traffic will be generated with minimum amount of packets. Okay, only duplicate at the point where we're going to branch to the location of destination. Okay, that will not generate the packet as the many of the destination. Okay, so you compare the traffic between the route multicasting and multiple unicast. You will see how much the traffic would be reduced. Okay, if you use multicasting. Okay, so main thing about multicasting is the concept that we deploy, which is the source base and group share tree. They have source base and group share tree. So source base means that every router will form the routing table for multicasting. So there must be all the address of the group inside the table and will determine what's the next hop. Okay, if we have to forward to next router or the local network that contains the destination of that group inside. Okay, you see that we have group 1 to group 5, and each group will list the next hop or how we forward. Okay, for example, group 1 in the router number 1, we will forward to local network, which is dash. Okay, this is the left hand side. And also we have to forward to router number 2 and router number 4. For router number 2 and number 4 to forward further. Whereas the other case, we use the group share tree. Okay, group share tree basically using the core router to perform the forwarding for us. Okay, so this one, the routing table of the core router must perform this forwarding. That's all for the multicasting. Okay, I think that's all for the data communication, which is a lot of details and content. Okay, and I have cut a lot of information already. Okay, so hopefully that everything would be useful for you somehow in the future. Okay, so as we say that the exam will 3 hours as before the multiple choice, 100 questions. Okay, and what's that? Open questions, the descriptive question, we have 3 + 1. And your friend asked me what would be the one question. I can say that one question is routing. So routing is very obvious, right? Okay, so hopefully that you can do the routing, but there will be what kind of routing that would perform. Could be distance vector, could be link state, right? Okay, so I think you have to check out whether you can do that. Okay. There you can bring in the calculator, but not the telephone. I think the university not allowed the telephone inside the examination room, but you can use the calculator, and hopefully it would be non-programmable calculator. 3 + 1, as I said, the 3 is the thing that we have discussed from the slide. Okay, but the other one would be open question, where I would like to see your it's kind of like a comprehensive exam where you can apply what we have learned. Okay, as an engineer, you should be able to think that if this is the characteristic of the problem or of the networks. Okay, yeah, that will be multiple choice and 4 questions of the descriptive. 3 plus. You have to do all of them. It's not the selection. You can select, but you're not gonna get the point that the question that you don't select. Sorry. There's no bonus. I don't think you're gonna have enough time to do bonus question because the extra question number 4 contain more score than others. ท่าน midterm เสร็จเร็วไม่ใช่หรอ but this one is easier that less descriptive because in the midterm some question may have the description like long writing, right? But this one seems to be more short answer or a very short description นะครับ choice okay I'll try to make the raw score of that and then we'll scale it down later. Okay, I think what I have said is the multiple choice is 1 score each, 1 point each, and for open question would be 20, 20, 20, 30. No, there's no 2-point questions because it's 100 already. In the midterm, I think we have 10 questions. It's 2 points, right? Okay. Any further question? Okay, we run out of time. โอเคไหมครับ Okay, before we go, as this is the first time that we have the on-site class, can I take picture of you guys? Because we're not going to see each other again, hopefully. I mean, not in the compulsory subject. If you're interested in the traffic engineering, okay, because Ajahn Chaudit and I will teach that subject in second term of the year 4, right? There will be half of the network optimization. Network optimization will involve the network optimization, for example, like shortest path, minimum spanning tree, minimum cost tree, something like that. Okay, so it'll be like learning about algorithm. Okay, not is easy part. Okay, and the Ajahn Chaudit will talk about the queuing. Okay, queuing theory, because this queuing theory used in the management a lot. Okay, in terms of manage the resource. Okay, manage the delay and queue. นะครับ so this is more in the elective. Okay, if you're interested. ครับ Can you get close in the middle, please? Move. Because I'm gonna be in there as well.แล้วผมอยู่ไหนดีครับเข้ามาครับ โอเค ตั้งเวลาก่อนนะครับเป็นครับ เดี๋ยวผมไปนั่งนู้นนะ แล้วผมข้ามไปด้วยผมตั้ง12เลย ผมไปอยู่ข้างหลังเรานะ ได้ป่ะครับ โอเค 10 9 ก่อนได้ไหมครับโอเคขอบคุณครับ ได้ครับ Okay good luck everyone for all the subjects นะครับเอาเองนะครับ
นอกจากเราติ้งมีอะไรอีกครับอาจารย์ขออีกข้อนึง
สำเร็จไง
ซับเด็กกับเราติ้งครับอาจารย์
มีปะวะสำเร็จ มีมั้งน่าจะมี เอ้ย2 อันนี้ต้องได้แน่ๆอยู่แล้วใช่ป่ะ
อะไรครับอาจารย์
2 อันต้องได้แน่
และอันอื่นนะครับอาจารย์
อันอื่น ๆ อันอื่นไม่รู้แล้วอะจำไม่ได้
โอ้อาจารย์
เยอะแล้วแค่นี้แหละอีกข้อหนึงก็ไม่ยากหรอก